All right, welcome to video 2.1. This is the first section of chapter 2. We're going to talk about sort of the basic unit of matter called elements and how they're arranged based on observable properties in this construct that we call the periodic table. And we're really getting at bigger picture questions in this chapter about what is the composition of the matter that surrounds us, all the solids and the liquids and the gases on this planet and in the universe more generally. How do we actually know that as scientists? How do we figure that out? And then how do we develop a common language so we can discuss chemical composition and maybe even predict how certain elements could interact or react with each other? And so that requires us to first start with this idea of what an element is. And so I think we all have sort of a basic intuition for what an element is, but let's define it in a true chemical construct. So this is the simplest, most fundamental substance that can't be broken down any further. So it can't be broken down any further into anything simpler. So this is the simplest sort of basic solid, liquid, or gas that surrounds us. Certainly elements can combine to create molecules which have more complexity and more diversity, but the element is the simplest sort of unit, basic unit of any type of chemical substance. And so we've got about 118 current elements. Several of those aren't that we're discovering new ones, but we're creating new ones in labs. We represent elements using a symbology of two letters, and we organize these things based on observable properties over the last several hundred years. And I'll talk in a second about the types of observable properties that scientists used to arrange these things into this thing that we now call the periodic table, which I think we all could recognize pretty generally. But we're going to talk about, well, why does the periodic table look the way it does, and how can we use that to have a general sort of qualitative understanding of how things might react. So the periodic table looks something like this. So all of the elements and their symbology, they have either one or two letter sort of abbreviations for the actual element that they constitute. And they're arranged in these groups, and we have either these vertical columns, which we call groups, or we have these horizontal organizations, which we call rows, or sometimes periods, either way. The periodic table then, with these groups and rows, are organized by, as I mentioned before, a set of observable properties that scientists looked at over the last several hundred years. And there's several different types of properties that exist that I have written out here. So we can have an intensive property. So those are properties of these individual elements in the natural world that do not depend on the amount of that particular substance. So if I look at, let's say, this particular element here, He, which we know as helium. We've all, or most of us, have probably experienced helium in an inflated balloon before. An intensive property of helium would be something like its temperature or its melting point that has no bearing on how much of the helium we have in the balloon, but is an intensive property to that particular element. Another example would be the melting point of, say, an ice cube in your refrigerator versus an iceberg in the Arctic Ocean. Both of these are made up of simple water molecules, and the melting point doesn't change based on the amount of those substances. So that's an intensive sort of observable property that scientists could have looked like. The opposite of that is the extensive property. So an extensive property is one in which it does depend on the amount of that particular substance. So something like the length, the volume, or the mass of that particular element, say the amount of helium inside of that balloon. does dictate these sorts of extensive properties. Um, Another, or sort of the two other big ones that really dictate the organization of this periodic table are physical properties and chemical properties. So in a physical property, these can be a little bit difficult to distinguish sometimes, but it's helpful to really separate these in our minds. Physical property is one in which there's no chemical change to that particular substance. And so one example is this melting of ice. So you go from water to water, but the physical state goes from a solid to a liquid. That's a physical property or physical change. A chemical property, though, is when there's an actual molecular level change in the chemical identity of a particular substance. And so really that's what constitutes the majority of this class are chemical property changes. And so a really simple example would be rusting, which we've all probably observed before, where you have pure iron to start with, which we call Fe, which shows up here in the periodic table. If we allow that to be exposed to oxygen environment for a period of time, what we observe is the formation of this new substance, Fe2O3, which we know as iron oxide, or more commonly as rust. And that's a chemical property. So it turns out that for the last several hundred years, chemists have really honed in on chemical property changes in different substances they found naturally. And the periodic table is a reflection of how different substances are similar or different from each other. And so these vertical columns, or these groups, are typically constructed because they have very similar chemical properties, or in other words, they react really similarly. And so you can imagine this as a puzzle back in the sort of early 1700s, when we only actually knew about 20 or so elements. Now we know 120. Much of this was undiscovered, but once the organization principles were established that these vertical rows had similar reactivity, even if things weren't discovered yet, say everything in this section of the periodic table hadn't been discovered yet, chemists and scientists knew that they were looking for something very similar to fluorine. And so that's sort of the basic construct. And we're going to spend several lectures talking about, well, how are these things similar and different in their types of reactivity? And so it turns out that the periodic table is really, really important for us to understand how these elements are organized, because it'll give us a lot of intuition for how we should be thinking about those individual elements going forward. So let's talk about the several individual groups. Remember, groups are these vertical columns in the periodic table that are constructed because of their similar chemical properties that they have. So let's start, and let's just go through each of the sort of key groups in the periodic table and describe some of the properties that they have. And so we're going to start actually with this group 1A right here. So that's this vertical group, and we call that group the alkali metals. And so I've got it highlighted in this smaller periodic table here in pink. So this is group 1A. We'll write that there. These are characterized by their soft, silvery surfaces. They're malleable, which means if you have a chunk of lithium or sodium or potassium, you can actually just squeeze it between your fingers. It looks like a metal, like an aluminum block, but it's soft enough that it cuts like butter. But one of the big sort of characteristics of group 1A is they're really reactive with water. So I will show you shortly a video of some of these alkali metals and their reactivities with water. Second, we have our group 2A. So now we've moved over one group on the table here. So we call these the alkaline earth metals. So these are typically characterized similarly. They're lustrous, which means they're kind of shiny when you shine light on them. Silvery metal-like in finish. They're still reactive with water and oxygen, uh, but less than 1A. The next key group that I want to talk about are the group 7A, which are right here. So that includes F as fluorine, Cl as chlorine, Br as bromine, I as iodine, highlighted also in the pink in this periodic table. So we call these halogens. They come from the Greek word halo, which means salt. So halo is salt, and that's because these are found as salts in nature, and we'll talk a lot about that in this class. So there's some sort of reactivity that these halogens go through that makes them end up as salts in nature. So we actually don't find much of these pure elements, if any of these pure elements, in the natural world, at least on this planet. The last key group that I want to talk about are the noble gases, which I think we've all heard before as well. These are group 8A, so they constitute this final column here: helium, neon, argon, krypton, xenon, and radon. So they're highlighted also as the pink portion of this periodic table, so noble gases. The name implies sort of two different things. One, all of these elements are found naturally as gases in the environment, which is different than, say, groups 1A and 2A, which are found as sort of the metals, and group 7A, which is found as a salt in a solid form. These are all gaseous in nature, and they're characterized by their very low reactivity, which is what gives them the name noble. Okay, so the other sort of general groupings that the periodic table gives us are by these bigger general categories, like metals, which are highlighted as the sort of pink constructs in this table. So you can see on the general full table, this black bold line here that I'm sort of highlighting in green, this is the boundary or the division by which everything in this center here are metals, and then everything to the right of this sort of staircase here, all of these elements are the non-metals. And then right in the center here on that division, highlighted in yellow in this table, we have these other types of this category called semi-metals. And so each is illustrated in their respective pink outlines. And just like the groups were delineated before, based on group 1A, the alkali, group 2A, the alkaline, earth metals, 7, the halogens, and 8, the noble gases, these groupings are similar in that they are grouped by similarities in the chemical properties that they possess. And so if we look first up here at this, the metals category, what I got are some images of, let's zoom in here, what I've got are some images of various metals, and you can see that they all have observable properties that are collectively pretty similar. So this chunk here, this black chunk, this is lead. This chunk here, these shavings are aluminum. This chunk is also aluminum. These shavings here are copper. This is gold. And this is iron here. And so you can see they're all sort of lustrous, silvery. They all conduct electricity. They are malleable, to some degree, which means if you pound them with a hammer, they will flatten out, they won't break like a brittle object. That may seem like a trivial point, but that's actually a really important point for this category of metals here. Non-metals in this sort of central region here, these can exist. Metals typically exist just as a solid phase, but non-metals can exist in all three phases, which is important. They're typically non-silvery as opposed to metals. They are brittle instead of malleable, which means if you hit them with a hammer, they'll usually break apart into smaller pieces. And they're most often non-conductive. So you can imagine scientists a couple hundred years ago, these are some pretty easy observables they were able to sort of generally group these elements into. And so if we look here, this flask, this Erlenmeyer flask is full of an orange liquid, but there's clearly a gas above it. This is bromine. It's actually bromine 2. They're bonded to each other. This is bromine gas. This is carbon. This is sulfur. And this is phosphorus, all in their elemental forms. And so we're talking about these compounds here. Okay. And last here we have the semi-metals. I don't have any pictures of these. These are some of the most interesting elements, honestly, commercially especially. These have properties that are, as you'd imagine, they're intermediate between metals and non-metals. So they are what we call semi-conductive, which means that they conduct electricity, but in only certain circumstances. And most of them are silvery. So if we go back up to our periodic table up here, this includes things like Si, which is silicon, boron, germanium, arsenic, tellurium, antimony. It turns out that these are most, if not all, used in modern electronic devices, semiconductor devices. So silicon, as you know, is what's used in primarily photovoltaic devices, but it's also the basis for all microelectronics that run the microchips and the processors in your phones. Germanium is very similar. Lots of microchips are based on germanium. Arsenic is often a component of really expensive, high performance photovoltaics, like on the Mars rover, we use a gallium arsenide or gallium antimonide. The same is true with tellurium and selenium. We often use cadmium telluride as a common photovoltaic. So just to zoom out here and give you a sense here, these are three big general categories that are different than the groupings in just the vertical columns of the groups based on the similarity in these chemical and physical properties that they have.